Hello and welcome to my presentation. My name is Alex Thatcher. I'm a Reservoir Engineer for Oilfield Production Consultant, OPC. We are a specialist provider of subsurface engineering, geosciences, and production engineering, and we support the upstream exploration and production sector. I'm presenting this material on behalf of Convolution Explorer, and Convolution Explorer is a novel new software for the realm of PTA. Today, I want to introduce to you Convolution Explorer and why we believe this to be the next step in pressure transient analysis. So to do that, I need to give you a bit of a theoretical history to pressure transient. So theoretical history of PTA. In the 19th century, we had Darcy's law, and that was flow in a porous medium. In the 1930s, we started doing water well drawdown analysis. In the 50s and 60s, we started focusing on build-up analysis, and that was typically using a Horner plot. That was a single constant rate drawdown followed by a build-up. We applied straight line analysis, generally by hand, to calculate our K and our skin. In the 1970s, superposition theory was invented. And this was to handle more real data that had many flow periods at different rates with many build-ups. There was a big advancement in the 1980s through the improvement of gauges, computers, and software, and Bourdais and others developed the derivative type curve analysis. And this was a fantastic development, as the derivative really allows us to see clearly the flow regime signal. In the 1990s, numerical Pebby grids were invented to handle more complex boundary configurations. In the 2000s, automatic pressure rate deconvolution on a single well basis was developed by Imperial College, and Levitan and Wilson implemented the first automatic pressure rate deconvolution algorithm in the software platform. And this brings me to Convolution Explorer. So ConvEx is a form of pressure rate deconvolution, but it does this in a much more robust way. And in fact, it doesn't do deconvolution, it does convolution, a single well and a multi-well basis. And that's the purpose of my presentation today, is to explain what Convolution Explorer, or ConvEx for short, is all about. And to help validate our results, Levitan has also developed a ConvEx 2D semi-analytical simulator, which again builds on numerical Pebby grids, where we start dealing with much more complex boundary configurations. And it's basically removing analytical PTA away from boxes. So PTA in an ideal world. So here I've created a synthetic channel with one well in the channel. You can see here the well B1, and it's in the middle of two parallel faults. It's closer to the south boundary than it is to the north. So remember, in the 1930s, constant rate drawdown analysis is the starting point for all pressure transient analysis. And the response perfectly traces out the reservoir. So what do I mean by constant rate drawdown? Well, what I mean is if I manage to flow well B1 at a constant rate for thousands of hours, what would the drawdown look like on a derivative plot? So let's do that. Let's trace out well B1 in this synthetic channel reservoir. So here you can see I have this black circle, which is the pressure propagation flowing well B1 at a constant rate. And at this point in time, we can plot the drawdown on the Bourdais derivative. So here we have the derivative, and here we have the dP curve. And you see that a zero slope on the Bourdais derivative tells us about our radial flow. And radial flow continues until it reaches these two parallel faults here. And once the pressure transient reaches those boundaries, we now have linear flow. And that's characterized by a half slope on a Bourdais derivative. And this linear flow continues until we see the boundary to the south, at which point the derivative upturns off the half slope trend. This continues until we see the fourth boundary in the north, at which point we reach a unit slope. And that unit slope is there due to compressible volume. So let's apply straight line analysis on this Bourdais derivative. We calculate that this field has a permeability of 500 millidarcies. The total skin is plus 2.75. Distance to these two faults is 1,600 feet, 3,000 feet to the south boundary and 8,000 feet to the north boundary. Analysis of the unit slope and lake time tells us the connected pore volume to the well is 4e to the 8 cubic feet, and converting that into stock tank oil initially in place is 34 million stock tank barrels. In reality, we never operate wells at a constant rate, and we end up with this variable pressure rate history here. And that's why in the 1970s, they came up with superposition theory to account for all these PBUs and different constant rates that exist in the data stream, because all these different pressure changes, rate changes affect this pressure data here. So here we started analyzing buildups, and here we have a 300-hour buildup. So let's calculate this in superposition time. So here we have the start of the buildup, here we have the end of the buildup. On the y-axis is the pressure data of this single PBU, but the x-axis is more of a calculation using these previous rate histories. So we see that the superposition plot is calculated. And therefore, if we take the derivative of this, we end up with this derivative here that lasts 300 hours. And this is a calculated derivative. So pressure buildups were used as a proxy for constant rate drawdown theory, but can cause complications in analysis. So now we are comparing the buildup in superposition time versus the constant rate drawdown in elapsed time. And I also want to introduce the concept of connected volume. So in pink, you see the constant rate drawdown in elapsed time, and in blue, you see the buildup calculated in superposition time. So let's work from left to right. So here we see wellbore storage and radial flow is pretty much the same. So we have good confidence in our permeability and our skin, regardless if we used constant rate drawdown theory or superposition time theory. So let's just quickly introduce radius investigation and the concept of connected volume while we're here. So here we can calculate a radius of investigation up to this point, and using that radius investigation in this formula here, we can calculate that radial flow sees 4 million stock tank barrels, which is useful, but the test has obviously seen much more volume than what radius investigation can calculate. And you can't really use radius investigation beyond radial flow because we no longer have that geometry of fluid flow. So it's only really valid up until the end of radial flow. So beyond radial flow, we quite clearly see the half slope for the parallel faults using the constant rate drawdown theory, but it's not so evident in the buildup calculated in superposition time. And that's because superposition time can cause distortions beyond radial flow. Another thing to note is that the constant rate drawdown derivative lasted an additional 3,300 hours of data. It's an extra log cycle, revealing all those valuable flow regimes. But the build-up derivative only lasts as long as you keep the well shut in. And if you keep a well shut in, you have deferred production, which is not great for economics. So we see that there's now a tug of war between the reservoir engineer and the production engineer about how long wells should be shut in. But we see that you have distortions beyond radial flow anyway, so do you really gain a lot of data by keeping the well shut in for such a long time? Perhaps. The other thing I wanted to mention that using constant rate drawdown theory, once you reach pseudo-steady state, you can place a straight line through those points, and from that you can calculate the connected pore volume to the well. For an oil well, this is the equation. And using that pore volume, you can quite easily calculate the stock tank oil initially in place. And like I said, for this reservoir and well, we see 34 million stock tank barrels of oil. So to summarize those points, a constant rate drawdown derivative adds more data to the derivative plot, provides much better definition and flow regime signal in the derivative plot, a better way to define connected volume to the well, and it does not require costly long buildups. So it would be great if we could somehow convert our data into constant rate pressure response. So let's go back to our variable pressure rate history data. And an equation that's been around for a very long time, but with no robust way to solve it, is the convolution integral. So let's quickly go through this equation. So PT is the observed pressure data, and that's this data measured by your downhole gauge here in blue. PI is your initial reservoir pressure, and that's the pressure before the start of any production. Again, that can come from your downhole gauge, or it could come from MDT data extrapolated back up to gauge depth. Q is your measured rate history here in blue. And PU is the unit rate response function, and it is a signature of the well and reservoir. And note the units PSI per stock tank barrel per day. So this is the important part of this equation, and it's the. So what is pressure rate deconvolution trying to do visually? Well, it's trying to convert this data here into this data. So that's the constant rate drawdown. And again, why do we want to do this? Well, if you took the derivative of this curve, you end up with the constant rate drawdown derivative that spans, in this case, 3,600 hours, and it gives us all those valuable insights into the reservoir. And just so you can visually understand what the unit rate response function PU is, it's this top curve here. And the derivative of the unit rate response function with the Bourdais derivative gives us all those valuable insights. It tells radial flow, the distance to the parallel faults, and ultimately how much connected there. Again, in reality, we have all sorts of problems, which results in failure of the automatic pressure rate deconvolution algorithm. So I took my synthetic data and I added in some noise to the data. So let's review some typical noise that you may see in real production long-term surveillance operations. So the first one I will start with is gauge noise. You know, our gauges are not perfect, but they are getting a lot better. But the big factor here really is gauge location. You know, our gauges are not located in the reservoir, they are located in the wellbore. And that can lead to wellbore effects, such as wellbore phase segregation and other noise that exists in the wellbore that doesn't exist in the reservoir. But remember, our gauges are located in the wellbore, so it's a bit of a tug-of-war between the wellbore and the reservoir. Another thing that can happen is tidal effects. So I added in some tidal effects. You can see down here, this sinusoidal pattern. And we see the sea level going up and down over 12-hour periods in our downhole gauges. And we see that when the build-up pressure change is comparable, very small changes, to the sea level going up and down. That's very typical. We can have errors in initial pressure. You know, we may have our downhole gauge, but at the start of production, you may still have wellbore completion fluid there, and you're not really reading true reservoir pressure, and that may mislead you. And we might have missing pressure data. So in long-term surveillance, you know, your pressure data your gauge might fail downhole. We may also have errors in rate measurement. I don't think anyone can confidently say they measure the rate from every single well in the field 100% accurately. And here you can see I make some subtle changes to my measured rate history. You may have cross-flow within the well between layers. So if you have a multi-layer reservoir and you have a long PBU, the build-up pressure may be distorted by the pressure change and the flow rate going from one reservoir to another reservoir within the same well. And you can also have a change in skin, very typical. So here you can see I've added in some noise, and that's what the noise has done to my derivative. So you see it's a bit scattered in radial flow. There's still a bit of an upturn in the half-slope trend. So now I bring you to deconvolution algorithms that have been around for quite a while now. And the first one I wanted to show you was automatic altogether deconvolution. So going back to the convolution integral, what automatic altogether deconvolution does is it feeds the algorithm the observed pressure data, the initial pressures, and the rate history. But the pressure data that it feeds to the algorithm is only build-up pressures, and it feeds all data from each PBU. So here you see I've got about 7 PBUs in the data stream. I feed them to the algorithm, and the algorithm solves for the unit rate response function. So let's do that. Let's feed this data into a typical deconvolution algorithm. and you get this response. So we see the end of wellbore storage is okay, and radial flow is okay, but I could have got that from a short PDU calculated in time. Beyond radial flow, we see the algorithm clearly failed. I mean, it's bending upwards, which is telling me something, but to get those clear flow regime signals of the half slope to the parallel faults, and the upturn from that indicating the third boundary to the south, and then ultimately what I wanted to know was the connected core volume. It's just not in this data stream. There's a lot of uncertainty in this data. So altogether, deconvolution usually fails for a number of reasons: changing wellbore storage, changing skin, due to the effects mentioned in the previous slide. So remember, those changes to the pressures, such as wellbore storage and skin, can affect the very early time pressure data of each PDU. So some clever people came up with what we call condition deconvolution. So we do exactly the same thing, but these pressures that we feed to the algorithm is the full pressure data from one PDU, but we end up feeding late time portions of the previous PDU. And that's to remove ourselves from any wellbore effects, changing spin, etc. So let's feed this data into the deconvolution. And you see it's a lot more stable, but it's still not good enough. It's not robust enough to tell us what's going on. You see here now there's a short upturn and then a stabilization that's very, very brief. Does that mean I'm closer to one fault and then I see the second parallel fault? What's going on here? Is this my unit slope, or is this last point my unit slope? This is not robust enough to really tell me what's going on. And diffusion does not really behave like this in the first place, with all these bends. Remember, diffusion is a slow process. So automatic deconvolution works better than altogether deconvolution, but uses very little data. Condition deconvolution can produce plausible results. However, a PTA model is needed to get the results, which in effect requires convolution. So the only way to check this response is to try and build a PTA model that goes through this derivative and compare how that PTA model would go through your full pressure and rate data set, which can become a tedious process, and not every deconvolution algorithm you'd be able to match with a PTA model anyway. That's where I bring you to Convolution Explorer, or ConvEx for short. So this is an interactive analysis tool that relies on pressure transient analysis. It's a dynamic behavior of oil and gas reservoirs. It can be done on a single well or a multi-well basis. And it's really the extension of PTA into long-term production analysis. And what we're trying to investigate is our understanding of geometry of fluid flow, reservoir connectivity, and large-scale heterogeneity. And ultimately, we may be able to find out the reservoir connected volume to the well. And having this information is really going to help us understand and optimize how our field development plan has been used efficiently or not. Do we have pockets of trapped hydrocarbons? What parts of the reservoir is more restrictive than other parts? This is ultimately going to drive how we develop our. So like I said, this type of analysis can be done on a single well basis and should definitely be used for exploration and appraisal well testing, but it can also be used in some development scenarios, such as a single well draining the entire reservoir, or a compartmentalized field with one well per compartment. It could be used on a connected reservoir which has dynamically divided into separate drainage areas, or it can be used on unconventional equipment without PDU. And like I said, this is also a multi-well tool, so it can be used on field startups, and it's during this initial startup of the field when you truly begin to understand how your field behaves. And this is the most important time of reservoir surveillance. And beyond field startups, it can be used in long-term production. You can monitor how your wells are behaving over much longer time. So let me introduce ConvEx to you now. and how it's different than automatic pressure rate convolution. So if we focus on the bottom equation again, remember this is the convolution integral. So what's different this time? Well, this time we are going to manually reconstruct the unit rate response function using this specialized software, ConvEx. And what we're going to do is, as we draw the unit rate response function ourselves, we are going to interactively solve for the pressure. So you see here, there's no fancy algorithms going on. There's not black box. This is very, here's what you draw, this is what you get going on. And now I'm going to explain how we draw the unit rate response function in the demonstration. But before we start the video, let me just explain what you see in the slide. So we set the initial pressure. We have our measured rate history in green. We have our observed pressure data in blue. Here we have the analysis pane. And over on the right-hand side, we have the build-up in superposition time shown in blue. And remember, this is noisy data that I'm using. And in red, on the top curve, we have the unit rate response function. And on the bottom red curve, we have the derivative of the unit rate response function. So what we're going to do is we're going to use the blue information, the build-up in superposition time, to help us draw the radial flow part of the response function. Now, if you remember on the earlier slides that I showed you, that there was no difference between the derivative calculated in superposition time and the constant rate drawdown derivative when we're looking at radial flow. So here we can use the build-up derivative in superposition time for the first maybe 5 hours. But then the superposition time, although it's noisy data, it still tells us that the derivative kind of upturns. So that's going to help guide us, but not exactly like what radial flow. So now, as we draw the derivative, that will have an impact on the unit rate response function. This will then be fed to the algorithm, and then we will calculate the pressure data based on the drawn unit rate response function. And we're going to see that match here. So with infinite acting radial flow with this level of skin, we see that we quite clearly have a mismatch between the observed pressure data and the results of this unit rate response function. You see here, there's not enough depletion in the system. So let's start the video. Now in green is what we have called control points. That helps us draw the unit rate response function. So here we draw the end of wellbore storage, we have the radial flow, and we set the skin between the wells. We can quite clearly see that there's not enough depletion in the system. We know that we have a fairly channel-like reservoir. So we anticipate that our derivative should begin to upturn. So what I do here is I set a 4-volume line, I anchor 2 control points to it, and that tells me that 442 million reservoir barrels, 4 volume. But that's not enough depletion in the system, so the reservoir must be smaller. So here you see I'm decreasing the connected 4 volume to the well, and how that affects our pressure match. You see here I made it too small. So I stopped at about 78 million reservoir barrels, and I go back to try and do my straight line. So here I set my radial flow line. With the noisy data, it's coming out at about 484 million. I go to my channel half slope. Like I said, the derivative is upturning, even though it's noisy data. My geologist tells me I'm in a channel. I set it about there, and I move my control points onto this one. Now you see with the 78 million reservoir barrels, I've got my short PBUs in the data stream that tells me that my connected bore volume is still too big. So you can see how accurate we have to be here. I change it to 74, still a bit too big. Finally, I change it to 72 million reservoir barrels, which is about 34 million stock tank barrels of oil. And now you can quite clearly see I have drawn a very smooth derivative. I've matched the radial flow, I have the half slope of the channel, I see the south boundary, and then I see the north boundary. You can also see that there are a lot of advantages over automatic pressure rate deconvolution, in that I can see the exact results of this unit rate response function compared to all of the flowing pressures, all of the PBU pressures. Remember, condition deconvolution would have this data for the final PBU and a very small pressure point. And I'd have no idea if the result was a good one. But here I quite clearly see the result of this unit rate response function, higher data set. So ConvEx is a much more robust technique to handle difficult data to solve the pressure rate deconvolution problem. But what about multi-well problems? So before we get into showing how ConvEx does it, I just want to show you what multi-well deconvolution is all about. So now you can see I have added in a second well, well B2, much closer to the north boundary and much closer to this east fault. The pressure and rate data for well B2 is now in pink, and for well B1 is in green. So on purpose, I kept B2 shut in for a very long time, just so you can see the effects of interference between B1 and B2. So as we shut in B2 and produce B1, we can see here the pressure at B2 starting to fall due to production at B1, not due to its own production. So all I was trying to do there was to prove to you that these wells interfere. I don't have any large fault going across the field that would separate these two wells. So the first starting point of multi-well deconvolution is to remove this interference. So what we were trying to do is convert this data into this data. So you see here now that the pressure at B2 does not fall due to the pressure at B1. So I'm trying to decouple the interference response between the two wells. So this is without interference, and this is with interference. So we are removing the effects of pressure interference between the wells. But we still have the variable rate history. So that's the next part of multi-well deconvolution. So we try to convert this data into this data, constant rate drawdown responses. And why do we do that? Well, if we take the derivative of this, we end up with these two unit rate response functions. And this can provide us a lot of valuable insights. So let's do that. What do I see here? I see the reservoir is extremely homogeneous. I get the same radial flow stabilization around B1 as I do as B2. I find that B2 has a higher skin in the well. Maybe that was due to a different type of completion being run. But that's good to know, and maybe there's some remedial actions that can be taken to reduce that skin movement. I find that B2 is much closer to reservoir restrictions. And then I can trace out the rest of the reservoir from the point of view of B1 and B2, but ultimately both wells see the field connected volume. What does that mean? If I lose one of these wells, I know I'm still connected to all that volume, so that volume's not been lost. That's reassuring. Whether you want to go re-drill that well, you'd have to look at the economics. So multi-well deconvolution attempts to remove the effects of interference between producing wells. This allows us to see the reservoir from the point of view of each well in isolation, allowing us to decouple all reservoir properties. So interference, how does ConvEx handle the interference? So let me go back to my channel reservoir. I have B1, and we're going to have a B1 self-response. We're going to have a B2 self-response, and we're going to have a third response, which is going to be the interference response. So this is due to the principle of reciprocity, and that means that the response from B1 to B2 is the same as the response from B2 to B1. Let's bring back up the convex pane. Let me just describe everything you're seeing. So in blue, we have the observed pressure data from the gauge for B1. We have the observed pressure data for B2. We have the rate history for B2. And hidden behind this panel is the rate history for B1. On this plot, I have the build-up of B1 in blue in superposition time. But remember, these build-ups will now be distorted by each other's production. So you're going to lose all that insight to faults, etc. In pink, I have the build-up of B2, of this build-up here. And again, it doesn't really show the correct flow regime signal. And that's because you have these dynamic boundaries created by the two wells. So what I've done is I've set up the correct self-response for B1, and I've set up the correct self-response for B2. And in red here is the interference response. And I've placed it down here on purpose. And what it basically means is there's no interference between the two wells. And to prove that, again, I'll go back to well B2 when it was shut for a very long time. And you can see that there's no pressure drop at B2 due to well B1. So in effect, drawing it like this is as if I put a big fault across the field. So now let's model the interference response correctly. So I'll start my video again. And there are some things you need to know about interference response. So if we reach pseudo-steady state, all responses meet at the unit slope in late time. And that's because once you're in pseudo-steady state, the pressure at every point in the reservoir declines at the same rate. You also have to understand that interference signals are delayed in time, and that delay depends on the distance between the wells and the reservoir properties. Also, due to diffusion, signals start small and they get bigger. So now what I do is I zoom in onto that period of time when well B2 was shut in for a long time. And this really helps us draw the interference response. And now you can quite clearly see which parts of the interference response affect which parts of the pressure match. So you see here I've got a slight mismatch during this earlier time, and with this curve, it's matched quite well. But you see this mismatch here. It's very hard to see. And that's because, remember, the interference response starts small. So I move my early time interference responses towards the right. You see I'm matching this part of the graph much better. And that effect has changed the late time response here. So we go back, we edit the later time of the interference response until we get a decent match. So now I zoom out just for the sake of time. You see this is the interference response, and I have now matched the pressure gauge data of both wells quite well. So here's just the summary again. So now we end up with the B2 self-response, we have the B1 self-response, and we have the interference response. And you can see that I have matched all the 3,600 hours of pressure data from B2 and from B1. I also look at the self-responses compared to the field map. And yes, that kind of makes sense. You know, we go for B1, I think it's in the middle of the two parallel faults, so I have radial flow and then I have an immediate half slope. Well, B2, that's different. It's much closer to a fault, and I have that fault being sensed much earlier in time. I also have the higher skin in well B2. So just to go over some of those points again, remember, after a certain amount of time, interference signals become comparable to the pressure effects of the well's own production. So in this case, that comparable effect is about 300 hours. So we see it starts small, and after about 300 hours, the pressure effects of interference is comparable to the self-responses of B1 and B2. If the reservoir reaches pseudo-steady state, all lines converge on a rate time unit slope. During pseudo-steady state, the pressure at any point within the reservoir declines at the same rate. Now, one thing in general about multi-well deconvolution is that the number of responses begin to escalate as the number of wells increases. So for example, if you have 5 wells, you end up having 15 of these lines. That's 5 self-responses and 10 interference responses. So it can become a tricky problem. Well, the next question is, yes, you have managed to replicate this 3 hours using these 3 responses. Although, yes, you've also constrained the early radial time parts using the build-ups in superposition time. Are there any other ways to validate our results here? The answer is yes, and this is why the ConvEx simulator was developed. So now you have my 2 wells, and what we do is, imagine if this was my actual field map. We draw our polygon over the the field map. Now, remember at the start of this presentation, I said it takes PTA away from boxes, but my reservoir is a box, so just bear with me for now. We add in our 2 wells in yellow. We set the properties of this polygon from the radial flow, gives me the permeability in the skin, remember. And my initial pressure, porosity, SW, compressibility, all comes from petrophysics and PVT. Then we run the simulator. Now what you see in black is the results from the simulator for well B1, well B2. What you see in blue is what I drew by hand. And you can see that it matches fairly well for the self-responses. For the interference response in the late time data, it's matched well. But on the early time data, it's not matched as well. But remember, the interference effects down here are very, very small and have barely any effect on our ability to match the overall pressure. So like I said, the semi-analytical uses a polygon, and it's to take us away from boxes. So here I show you a real case study. We have a real channel, and we've drawn the polygon that reflects this real channel. So based on the convex analysis of this field, OPC deduced that the connected volume is greater than that on the map, and perhaps the reservoir extends beyond what is mapped. And this helped the client reevaluate their FTP, and in particularly injection planning. So some general statements about the simulator. The 2D semi-analytical simulator is incredibly fast to set up. It does not have the computational penalty effects of gridding, and it gives high quality pressure transient results without the gridding effects. So here's another example just to show the convex simulator in a bit more detail. So this is a map from SPE 195904. It's a very good paper. I very much recommend reading it. It's about multi-well deconvolution. But OPC did their own study on this field. And just to show you the polygons that we have at the time of our analysis, this is the polygons that we drew. So each polygon has their own properties, e.g. KH, skin, pore volume, etc. The reservoir shape is no longer constrained by 4 straight line boundaries as per classical PTA. The polygons shown add up to the minimum connected volume at the time the reservoir had reached pseudo-steady state. So with more production in time, the full reservoir signal may manifest itself in the pressure and rate data, and these polygons would expand. And this ultimately allowed the operator to optimize the FTP and identify any pockets of gas not connected to the wells. So I want to show you a real example using ConvEx. So this is a single gas well in a reservoir compartment. So this is a multi-well reservoir, but our analysis showed that this well in the reservoir is not connected to any of the other wells. So it's a high productivity dry gas well. The reservoir pressure declined from 6,300 psi to around 1,500 psi. There's a good sequence of short PDUs to help guide early and late time response functions. The gas PVT varies, and this is accounted for by pseudo pressure and material balance pseudo time. And we've also accounted for the rate dependent skin. But there was a lot of problems with this data. We had poor pressure data over here. So you have a PDU and then something happens, and this data we also have missing pressure data, and perhaps there was rate allocation errors over here. But using ConvEx, we managed to see all this, and we managed to extract a reasonable unit rate response function. And you saw we see very quickly, we see a fault, and we see a second fault, and ultimately we see the pseudo-steady state, and we get the connected pore volume and the gas connected to this well. Extremely useful for FTP and management of this reservoir. So another advantage of the way ConvEx works is that we can actually forecast, and it's very simple. I go back to my synthetic data with the 2 wells, and we set the forecast period. So in this case, I set the forecast period for about 2,000 hours. I constrain the bottom hole pressure with these control points. So I'm saying if I want the reservoir to decline like this, what would be my rate? But also we have to extend the response functions. So in this case, my reservoir was in pseudo-steady state, which means there's a unit slope in late time. So pseudo-steady state would continue for the 2,000-hour forecast time. And from that, ConvEx will calculate the rate, taking into account the interference of the wells, reservoir architecture, how each well would be operated, bottom hole, and this would be the rate. So ultimately, though, you should still make a full field numerical simulation model. But ConvEx can be an extremely useful tool to help you build your simulation model at the start. So here I have my channel reservoir, for example, and this is how I would use ConvEx to history match this model. So I would run B1 only at the unit rate response function and calibrate the model to ensure the ResSim model overlays PU dash and PU. What do I mean by this? So I add in one well, B1, I run it at the constant rate, I take the drawdown, and I take the derivative. So in pink, if you imagine, is my derivative from the reservoir simulation model. And in blue is the derivative that has been calculated as a self-response from multi-well convolution from ConvEx, which I showed you on the previous slide. And this is such a good history matching parameter. Let me explain why. This plot, what does this tell me? Well, this tells me that the connected volume of my ResSim model is too high, but it doesn't tell me by how much. And why is my flowing pressures off? Is it because my permeability is too high? Is it because my skin is not high enough? Or is it just because my connected volume is too high? This plot does not tell me that on the left. This plot, on the other hand, decouples everything. So it's telling me that my permeability is too high, and it's telling me my connected volume is too high. But if I use straight line analysis on this point and the blue data for the correct match, it can tell me by how much off it is. So for instance, if this told me it was 50 million stock tank barrels of oil, but it should have been 34, it tells me by how much I need to reduce the stock tank barrels of oil by. Likewise for the permeability. So if I fix these two things, I can run it again. Then I can check what the skin at the well is, and I can do all this iteration. Finally, I end up with this response. Now, if you can match this response, you can match this response. So this is a much better way to do the history. And remember, this is now constraining the geological model, as I've removed the interference between the two wells at this point in time. So then what I do is I remove well B1, and then I place B2, and I do the exact same procedure. I run B2 at its constant rate drawdown, and I take the derivative. And for well B2, I find that the permeability is too low. So again, I'd have to fix that, change the geology around the well, etc. But ultimately, the connected pore volume should be correct because I would have history matched that when I history matched well B1. So again, you'll do your history matching, and you end up with the responses overlaying. Finally, just to validate all of this, you add in the two wells, you run them at the variable rate history, you simulate the pressures, you perform multi-well deconvolution, and these responses should overlay now the responses that you got on the observed pressure and rate data, multi-well deconvolution analysis. So to summarize, constant rate drawdown theory developed but never achieved in the field. Build-up analysis using superposition time used as a proxy for constant rate drawdown analysis, but complicates analysis. Automatic pressure rate deconvolution was developed, but is not robust enough to deal with noisy data. Manual reconstruction of the unit rate response function was developed to deal with noisy data and provides a deep understanding. This was extended to multi-well problems. The ConvEx 2D simulator was created using polygons over the 2D field map to take analytical PTA away from boxes and to validate our multi-well or single well convolution results. And unit rate response functions are a smart way to calibrate the geological and dynamic simulation model. ConvEx success stories. So we've now used it all over the world on some very big fields, such as the Guyana Liza project in Suriname. We've used it in West Africa, the Middle East, USA, UK. And a really good paper that you should read is SPE 195441 on Tamar Giant Gas Field. So from this, it was 5-well development. Early on, the field behaved as a single-phase reservoir with negligible aquifer pressure support. We determined 2 reservoir subsystems, not in pressure communication. We determined the connected volume to all wells. We identified which wells received edge water drive and which received bottom water drive. We quantified the level of aquifer support to each well. We did all this along with the usual KH, skin, distance, default, etc. So this ultimately adds significant value to the operator and will really help them manage the field development plan and optimize the asset going forward. So thank you for listening. Some additional papers that I recommend reading are down here, all about multi-well deconvolution. If you have any specific questions, you can email myself, Alex Thatcher at opc.co.uk, or please contact Mike, who has been a figure in the development of deconvolution, and he's a real expert, and he is the man who developed Convolution Explorer. Thank you for listening. Goodbye.